Welcome back to our course, Fundamentals of Operating Systems, based on the text Operating System Concepts, 10th edition, by Abraham Silberschatz, Greg Gagne, and Peter B. Galvin, published by Wiley Publishing. In this unit of our course, we are discussing process synchronization. The issue here is that multiple processes, possibly on multiple processor cores, are all interacting and perhaps sharing common resources such as memory addresses. And the issue is to try and prevent the processes from interfering with one another during the course of all this. Now, in the first part of this unit, we discussed the testing set. Testing set's a special assembly language instruction that does two operations atomically. That is, the instruction cannot be interrupted in the middle, and it is not necessary to disable interrupts. Testing set is a privileged instruction that requires supervisory mode permissions. Next, we talked about mutex locks, which are considered to be the simplest of the synchronization tools. Now we're going to talk about a more robust tool that can behave like a mutex lock, but can also provide more sophisticated ways for processes to synchronize their activities. So let's get started. A semaphore is an integer value that, apart from initialization, is accessed only through two standard atomic operations: wait and signal. Semaphores were introduced by the Dutch computer scientist Edgar Dijkstra. You may remember Edgar Dijkstra from your early computer classes as the man who created the term spaghetti code to represent the poorly structured programming of the day. We owe a great deal to Dr. Dijkstra's observations, which led to the modular programming that you were taught. The wait operation was originally termed P for the Dutch proberen, which means to test. Signal was originally called V for verhogen, which means to increment. The definition of wait is shown here, followed by the definition of signal. All modifications to the integer value of the semaphore in the wait and signal operations must be executed atomically. That is, when one process modifies the semaphore value, no other process can simultaneously modify that same semaphore value. In addition, in the case of wait, the testing of the integer value of S, as well as the modification S decrement, must be executed without interruption. In other words, the testing and then the decrementing. Let's talk about how semaphores can be used. Operating systems often distinguish between counting and binary semaphores. The value of a counting semaphore can range over some unrestricted domain. What is a domain? Well, in mathematics, a domain refers to a set of elements to which a mathematical or logical variable is limited. In other words, 0 to 50 or 0 to 100. The domain of the year, would you say, is 12 months, January through December? How about a deck of cards? We could say it's 52 divided into 4 suits of 13 cards each. That's the domain. So accounting domains can range from 0 to some number. On the other hand, the value of a binary semaphore can only range between 0 and 1. Therefore, binary semaphores behave like mutex locks. In fact, on systems that do not provide mutex locks, binary semaphores can be used instead for providing mutual exclusion. Counting semaphores can be used to control access to a given resource consisting of a finite number of instances. In the case of the counting semaphore is initialized to the number of resources available. Each process that wishes to use a resource performs a wait operation on the semaphore, decrementing the count. When a process releases a resource, it performs a signal operation incrementing the count. When the count for the semaphore goes to 0, all resources are being used. After that, the process that wishes to use a resource will block until the count becomes greater than 0. We can also use semaphores to solve various synchronization problems. For example, consider two concurrently running processes. Process 1 with a statement S1 performing some operation, and process 2 with a statement S2 performing some other operation. Suppose that we require that S2 be executed only after S1 has completed. How can we do that? We can implement this scheme by letting P1 and P2, process 1 and process 2, share a common semaphore. Let's call it sync, which would be initialized to 0. In process 1, we insert the statements in S1 and then signal sync. In process 2, we insert the statements wait sync and then S2. Because sync is initialized to 0, process 2 will execute wait sync only after process 1 has invoked signal sync, which is after statement S1 has been executed. In other words, how could process 2 execute wait sync when sync is equal to 0? So you see, sync is initialized to 0, so process 1 must execute first and then increment sync to 1 with the signal operation. Only then can process 2 decrement sync with the wait operation and execute a statement. Let's create an image in our mind that might represent this. Those of you who have been in the U.S. have probably come to a road maintenance site where one lane of the road has been closed for repair. That forces the cars moving from either direction to share one lane. Now you have found that at each end of that section of road being repaired, there's a flag man. We can create a semaphore for this action and call it safe to go. Traffic moving from your end to the other end could be process 1, and traffic moving from the other end to your end could be process 2. When you arrive at the flagman on your end of the road, you may have the sign pointed to you saying stop. We will use 0 to represent stop, so you are blocked from the common section of road. Cars are coming from the other direction. When the flagman changes the sign to go, or slow, which is what it usually says, then you can go, and the cars from the other end must stop. We'll use 1 to represent go. Now what has happened is, while you were waiting, the sign man at the other end performed a wait, changing his sign to stop or decrementing to 0, making all traffic coming from his end stop. Dijkstra would have referred to this as a V operation. Then when the sign man on your side of the repair area sees that the path is clear, he performs a signal, changing his sign to go or incrementing to 1. Dijkstra's P operation. It's important to note that nothing can happen until both sign men perform their operation. That means it's atomic. So the two sign men represent the wait and signal operations on the semaphore safe to go. They will appear to have executed atomically. Now I'll have to wait for some feedback to know if that analogy has made any sense to you, so let me know. Okay, we have been introduced now to the semaphore. Now the semaphore is a very important structure in process synchronization, and it's a topic that you need to have a firm understanding of. So let's take a break here, take a look at your notes, go back over this stuff and make sure you got it down pat, because we're going to continue our discussion of semaphores in the next lesson.